Gears are used in a wide range of torques, speeds and gear ratios. Hence the varieties of gears. Whether they are the smallest or the most bulky, these are mechanisms that almost no car can do without. Their durability and reliability largely depend on the correct calculation and design of gears. To transfer movement between parallel shafts, cylindrical wheels are used, straight-toothed, oblique, chevron. When the axes intersect, conical wheels are used. They can be straight-toothed, with an oblique tooth and circular. Helical and hypoid wheels transmit motion between the shafts, after which they intersect. Wheels with external and internal gearing are often used, in particular in planetary gears. For the normal operation of the transmission, the profiles of any teeth must be conjugate, that is, they must provide a constant gear ratio. Among the numerous curves that make it possible to perform such a conjugation, the involute of circles has been extremely widely used. The involute is a sweep of the main circles. Let's consider the main parameters of the gear wheel. Denote the diameters of the main circles dB1 and dB2. Center distance A to B. The circle along which the tool is rolled during cutting is a dividing one. And the circle along which the wheels are rolled during rotation is the initial one. These circles D1 and DB coincide with the gears without displacement. The driving and driven wheels rotate, as a rule, at different angular speeds. The ratio of the diameters of the initial circles is determined by the gear ratio. For the normal operation of the transmission, the equality of the circumferential steps of a pair of gears is necessary. The circumferential pitch is the length of the arc between the tooth profiles of the same name along the initial circle. The circumferential pitch of a straight-toothed gear wheel is equal to the ratio of the circumference to the number of teeth. This value determines the circumferential modulus, the main characteristic of the size of the teeth. The diameters of the circles, protrusions and depressions limit and determine the height of the teeth. Now let's go directly to the main parameters of gearing. The geometric location of the contact points of the mated tooth profiles is the engagement line of the CCC1. This is the tangent to the main circles. The point of intersection, the line of engagement with a straight line connecting the center of the circle, is called the pole of engagement. Alpha double to the engagement angle. The active section of the FF1 engagement line is bounded by the circles of the vertices of the gear teeth and the wheel. It is on this site that the involute engagement works. The dividing circles, the width of the tooth and the cavity should be equal. However, the thickness of the tooth decreases when cutting by the amount of the guaranteed lateral gap delta, C, teeth distinguish between the head and the leg. For the normal operation of the transmission, the next pair of teeth must engage before the previous one comes out. To do this, the length of the active section of the engagement line must be greater than the main step. Their ratio, that is, the epsilon alpha end overlap coefficient, should be greater than 1. We have examined the geometry of the gearing. Let's move on to the loads on the tooth. In engagement there is a force normal to the surface of the tooth Fn. It causes contact tension. The roller analogy will explain how contact stresses arise. In the absence of external forces, the rollers contact along the line. We will apply the force of Fn. The rollers are deformed, an elastic contact pad is formed. There are tensions in the contact. The magnitude of the contact stresses is calculated according to the Hertz formula. It includes the normal force, the reduced elastic modulus of the roller materials, the minimum length of the contact lines and the reduced radius of curvature of the rollers. As the minimum length of the contact lines decreases, the contact voltages increase. With the same materials of the rollers, the reduced modulus of elasticity is equal to the elastic modules of the rollers. For various materials, the reduced modulus of elasticity is determined by the formula. Changing the radii of curvature of the rollers leads to a change in the width of the contact area and, as a consequence, to changes in contact stresses. Let's get acquainted with possible damage to the working surface of the gears. If the contact voltage exceeds the permissible one, fatigue crumbling occurs. Using the example of two rollers, one of which rotates slower and the second faster, you can show the mechanism of fatigue crushing. On the leading surface, the friction forces and cracks are directed against the movement. It is lagging behind in movement. When oil penetrates into a crack on a lagging surface under pressure, the crack closes. High oil pressure bursts the crack walls. So the fatigue crack develops into a sink. On the leading surface, the inner end of the crack first enters the pressure zone. In this case, the oil is squeezed out and the crack does not grow. Since the lagging surfaces are the teeth legs, they are crumbled first. In heavily loaded gears operating with insufficient lubrication, a metal contact occurs between the teeth, which, under conditions of local high temperature, leads to molecular adhesion of the tooth surface. Pieces of metal break out of a softer surface and firmly grasp a harder one. When rolling with sliding on a pared tooth, they furrow its surface. This form of jamming is called bullying. Abrasive wear is a type of damage characteristic of open gears or gears that are poorly protected from contamination. One of the dangerous types of destruction is tooth breakage. It comes from significant bending stresses occurring at the base of the tooth. These are the main types of damage to gears. In application to gears, the Hertz formula has the following form, where the reduced one is the reduced radius of curvature at the gearing pole. RO1 and RO2, respectively, are the radii of curvature of the gear and wheel teeth. In the engagement field, the zones of two-pair and single-pair engagement are clearly visible. The zone in which one pair of teeth works is the most dangerous for straight tooth engagement. Therefore, the calculation is made by the engagement pole. The minimum length of the contact lines of engagement is equal to the width of the wheel. When calculating the gear train, it is necessary to take into account the dynamic load arising in the engagement and the mutual misalignment of the teeth. The nature of the dynamic load is explained by errors in the manufacture of gears and elastic deformations of the teeth. If PB2 is greater than PB1, there is an edge impact of the teeth. When PB1 is greater than PB2, the median impact in the calculation of the gear train for strength, the presence of a dynamic load is taken into account by a special coefficient kV greater than 1. When the shafts and supports are deformed, the teeth are skewed, the load is distributed unevenly across the width of the tooth. The unevenness of the load is taken into account by the coefficient K beta. The calculated load is entered into the Hertz formula. Ultimately, when calculating gears, it is necessary to take into account the material, gearing geometry and design load. All this is reflected in the transformed Hertz formula. Let's consider the features of the skew gear operation. Its advantage is that there are always several pairs of teeth in the engagement. The total length of the contact lines is much longer than in a straight tooth transmission. The radii of curvature of the teeth are also larger. This determines the increased load capacity, lower dynamic load, smooth operation and noise reduction. The peculiarity of the oblique engagement is the presence of axial force. There are no axial forces in the chevron transmission, since they are mutually balanced on both halves of the chevron. When working in a bevel gear, several pairs of teeth are involved simultaneously, so it is necessary to take into account the uneven load distribution between these teeth. The coefficient K as alpha is additionally introduced into the calculation formula. In addition to calculating the contact strength, it is necessary to check the tooth for bending endurance. In polarized light, it is clearly visible that it is at the foot of the tooth in the loaded transmission that the maximum voltage occurs. In the presence of significant errors of the main step, the entire load is applied to the edge of the tooth. This is the worst case. The teeth in the dangerous section are simultaneously compressed by the force of the FR stroke and bent by the moment of the F stroke multiplied by L. Although the stress on the stretched side of the teeth is less than on the compressed side, the development of fatigue cracks occurs on the stretched side of the tooth. The effective stress on the stretched side of the tooth, taking into account the stress concentration at the root of the tooth, is determined by the formula, where YF is the coefficient of the shape of the tooth, which determines its strength. Changing the area of the dangerous section of the tooth affects its bending endurance. Having done the basic calculation of the transmission, we can proceed to the manufacture of gears. There are two main methods of cutting teeth. The method of dividing with shaped cutters, the method of rolling with a chisel and worm cutters. Wheels are cut into a variety of sizes. Currently, it is difficult to find a car in which gears are not used in one form or another. They work underground, on its surface and in the air.